Just take a few seconds to present today's speaker, which is one of those people you need not to present. So that's an easy situation for me as a host of this meeting. Johan van Benthem is a well-renowned scholar in many fields, and particularly in the field of epistemic logics in general, dynamic logics, and so on and so forth. And we are very happy that we finally managed, after a long attempt that has taken a few times and the pandemic in between, we are very happy to finally have the opportunity to host his talk. And the title of the talk is perfect for the setting, since, as some of you already know, this seminar is hosted as one of the activities related to a project that is a joint project between the Department of Philosophy and Department of Economics. We have Alessandro Gioffre, which is a co-worker of mine in this project. And so it is a project that features occurrences of logic issues and game theoretic issues due to the two research units that are involved. And the title of the speaker, Interfacing Logic and Game, sounds very nice for this setting. So I thank you again, Johan van Benthem, for being here, and I leave him to start the talk.
Right. So thank you, Ricardo and Alessandro, for inviting me. It indeed looks like a congenial project. Of course, I regret that I wasn't able to actually come to Florence, especially since it must be very nice now without foreign visitors. So maybe there's a sort of logical paradox here. If logicians want to visit Florence devoid of foreign visitors, maybe that's logically impossible. It's also nice to talk to an Italian audience, because actually in my work in logic and games, I've always been inspired by, on the one hand, some Italian economists / game theorists like Giacomo Bonanno and Nick Dimitri. And of course, on the other hand, I have long-standing connections with the flourishing Italian logic community. That said, that my purpose for this seminar is rather simple. I'd just like to talk a bit about interfaces of logic and games. That's a very big topic, so I'll take a few items here and there. My slides have more information, and they also have further references. I can say beforehand that behind my presentation, there's a book, a monograph that I've written, Logic in Games, which came out with the MIT Press in 2014. And if you don't like reading books because they're too long, then actually there's the Stanford Encyclopedia of Philosophy, which has a survey article on logics for analyzing games, which I wrote together with Dominic Klein, and where you can find a lot of material and references too. So whatever I say, there's that literature. Why am I interested in the connection between logic and games? Well, in the background is a sort of general view of logic that I have a sort of idea that logic, if you look historically, has actually two aspects, or there's two perspectives you could have on what logic is analyzing. On the one hand, it's description of the world, so tracing the structure of reality and valid reasoning about that. But on the other hand, it also has its origins in conversation, argumentation, dialogue. So in that sense, logic is also about a social activity, namely communication in rational manners. The two perspectives are not at odds, they're complementary, and often it's the same sort of mathematics that gives you a good view of both. That's just for background. Now, in the first part, I'd actually like to talk a bit, with apologies to those who know things like this, a bit more concretely about encounters between logic and games. So notions and topics in the two fields have connected historically, if you look at the past century. And I just want to give a few illustrations to see why it's a natural combination. Illustrations that actually lead to all sorts of open problems still right now. For instance, it's very possible to think about basic notions in logic in terms of a game. And the famous and much used are so-called evaluation games. Evaluation games are played with a model, so a mathematical structure standing for some situation, and a formula phi, and then maybe there's also some auxiliary things. For instance, when you do evaluation games for first-order logic, then you actually have a model, an assignment S, which is a function from variables to objects, and a formula. And the game is played between two players, verifier and falsifier. Verifier claims that the formula is true, falsifier claims that the formula is false. So truth and falsity belong together in this game, and we actually analyze truth and falsity in terms of moves in a game. What those moves are depends on the structure of the formula phi. So for instance, if the game is about some atomic statement, let's say PD, so just object D has the property P, then that's just a test whether that's true or not. Verifier wins if the atom is true, falsifier wins if it's false. Couldn't be simpler. So just that's according to the facts of the situation. But as soon as you look at the logical operations, they fit very natural with a game explanation. For instance, a disjunction phi or psi. So verifier claims that either phi or psi is true. In the game, this translates into a choice. So at this stage, when it's about phi or psi, verifier has to make a move and choose which disjunct to play. So is he going to defend phi or is he going to defend psi? So this is a typical game notion, choice. Now this is a choice for the verifier. Could there also be a choice for the falsifier? And the answer is yes, because that's exactly the duality we have in logic between disjunction and conjunction. So when there's a conjunction, verifier doesn't have to make a choice, because verifier claims the conjunction is true, so verifier claims that both phi and psi are true, so there's nothing to choose. But falsifier claims that the conjunction is false. What that actually means is that falsifier claims that at least one of the conjuncts is false, right? You say you can't have them both. Well, then falsifier has to choose which conjunct to play. So we've dealt with two basic logical notions now. Now another one, negation. In a game theoretic setting, it's very natural to think that actually negation is a switch of the roles between the two players. If the verifier defends that not phi, then actually, if the game was not about not phi, but about phi, verifier would be attacking phi. So the verifier in the not phi game is the falsifier in the phi game, and vice versa. Role switch. And this can be extended to existential quantifiers in a way which I'm not going to explain in detail, but basically, the basic operations of first-order logic can be explained as moves in an evaluation game. And in particular, you get a sort of new view of logical operations, they're game actions. And one reason why in logic you see these strong dualities between, say, conjunction and disjunction, or universal and existential quantification, is that from a game point of view, these are really the same game operations. The only thing that's different is which player does them. Now, these evaluation games connect in a very natural way with the standard logical notion of truth. The first order formula phi is true in a model M, and now I suppress the assignments, that's not so important for the point to be made, if and only if the verifier has a winning strategy in the game which I just described. So here what we tie together is a logical notion, truth in a model, and a game theoretic notion, winning strategy. This is an insight due to Hintika and many other people. Actually, often when I give talks, I meet new people who claim that they were the first to see this. But it's a sort of simple but important insight. Now, through this connection, the natural connections between games and logic quickly broaden. Because if you keep this fact in mind, you will also see that logical laws start saying something about games. Take, for instance, the law of excluded middle. So phi or not phi is true. Well, it's actually valid. What that means is that in every model, phi or not phi is true. At least if we're talking about classical logic. But that actually has a game theoretic meaning, because what it means is that if you play any game of this sort on any model, well, how will that game go? It starts with a disjunction, so that's a choice for verifier. Verifier can choose to play the phi game, which means that verifier is going to play the phi game as verifier. Or verifier can choose to play the not phi game, but through the switch. That actually means that verifier chooses to play the phi game as falsifier. That's just through the explanations which I've given. And the fact that there's always a winning strategy for this phi or not phi means that it's got to be the case that in the phi game, and that's an arbitrary phi game, either verifier has a winning strategy or falsifier has. So then the game theorist will say, aha, I understand that. That means that evaluation games are determined. One of the two players has a winning strategy. In this game, either the verifier or the falsifier. And this can be tied to a very early game theoretic result. Some people think of this as proto-game theory, some game theory before game theory. A famous theorem by Zermelo, one of the founders of modern set theory, who actually proves that two-player zero-sum games with finite depth are determined. Now, I'm not going to go into the details of these notions, but basically, I think the verification game is a good example, the evaluation game, because there's two players, verifier and falsifier. Zero-sum, because there can only be winning or losing. And there's finite depth, because the depth of the game depends on the logical operators in the formula. You unpack them in the game, so at every move, the formula gets simpler. You lose at least one logical operator. So there's a finite depth to the evaluation game, predictable from the form of the formula. So it's got to be determined also for this general reading. Well, the proof of Zermelo's theorem itself has some logical interest, which I won't go into. I refer you to this literature. And of course, the proof of Zermelo's theorem also stands for lots of developments, both in game theory, but also in computer science. So game solution algorithms are often like the algorithm that Zermelo gave. This is, one of these interesting coincidences, but unfortunately, okay. Zermelo's theorem was actually rediscovered by Max Euwe. Max Euwe was actually a Dutch world champion in chess, because you may not know this, but for 1 year in history, Holland actually had the world champion in chess. I think this was around 1929, something like that. Max Euwe actually beat the then Russian world champion. Unfortunately, it was a rematch, which he quickly lost. So Holland only had the title for 1 year. And so that was one blow. And the other blow was that Euwe actually published this theorem, and then it was pointed out that Zermelo had already proved it. On the other hand, it's interesting that a world champion in chess would actually have this mathematical interest. There's more to say about Zermelo's proof, which I won't do. If you actually want to analyze it well, you quickly get into more complex logics, so-called fixed point logics that I may say something about later. That has something to do with the nature of the solution algorithm. But the other connection I'd like to explain is, I'll take another logical law, again to show you how quickly it's possible to actually move from simple logical laws, or thinking about simple logical laws, to issues about games. Take the propositional law of distribution, which says that P and Q or R is equivalent to P and Q or P and R. It's classical propositional logic, that's valid. Now, the two trees that I've drawn for you here are the shapes of the evaluation games for these formulas. Like to the left, I write A here, that should be falsifier, and when I write E, that should be verifier. But it starts with a choice for falsifier between P, the atomic game P, or handing the turn to E, so the verifier, and then E has a choice between Q and R. The same explanation to the left. And now you might ask yourself, just as a sort of independent thinker, I see two different extensive game trees. Are these two games the same? The logical law of distribution would suggest maybe that they are. right? Since in distribution, these two formulas are valid. These two formulas are logically equivalent. Well, that's sort of interesting. We immediately get into very interesting issues because the answer is yes and no. It's definitely true if you only care about the control that the players have over outcomes of the game. Because then you could say the control which A has over outcomes in the game to the left is A can force the game to end in P, or he can force the game to end in QR, namely by giving the turn to E and then letting E choose. If you look at the powers for A in the game to the right, well, he actually has 4 strategies in the game to the right. If he chooses left both times, he forces the outcome P. So that's like the power he had on the other side. If he chooses right both of the times, he forces the set of outcomes QR. Notice he cannot do better than that because, of course, A can choose the strategy right, but of course it depends on E whether that's going to end in Q or in R. So right gives A the power QR. And then there's a few intermediate powers. For instance, A could have the strategy left-right. That will actually allow him to force the set of outcomes P and R, but that's subsumed by the fact that he can already force the game to end in P. So from a sort of power analysis, control over outcomes, you'd have to say that these two games are the same. But of course, it would be equally reasonable to say that you don't find them the same, because if you look at the internal dynamics and the choices of these two games, there are some very striking differences. For instance, in the game to the left, what can happen is that E reaches a point where it's totally up to E to decide whether the game ends in Q or R. That happens in the tree to the left. But to the right, there is no such point. Because when E is at the root, E certainly does not have the power to make sure that the game ends in Q or R, because it could end in P, depending on what A does. And if you go lower down, let's say to one of the A nodes in the tree to the right, then again, the choice made by A, it's not the power of E to offer that choice. So in other words, there's a natural alternative. You might actually look at how the game is played, look much more finely, look at players' actions and choices. Then you'd have another notion of game equivalence. That actually, given my analogy with logical laws, that actually means that laws of different logics could actually correspond with different game equivalences. And that leads to the sort of very interesting duality, you might say. You could think about different logical systems. Say in quantum logic, you don't have distribution. Okay, so you would have different games. And of course, on the game theoretic side, this correlates with the fact that there's not one unique view of when games are equivalent, because game theory offers options, extensive games, which would be closer to this action and choice level, strategic form games, and so on. That's all I want to say about these first connections. So if you take the evaluation game as an example, you see that a logical notion, truth, correlates very nicely with a game theoretic notion, winning strategy. And through that connection, you will actually see that there's a sort of natural analogy between thinking about logical laws and thinking about game equivalences. But there's more to be said from a logical perspective. So, of course, because so far I've only talked about game forms, but games are, of course, played by players. And the agents that actually play games are of interest and raise lots of logical issues themselves. By the way, just to stress this slide, I talk as a logician. Does that mean that I think that everybody should think like a logician? No, that would be actually pretty bad for the university. I'm only trying to convey a sort of logical viewpoints on these matters. But of course, game theory also has a lot to say. Economists have a lot to say, and so on. It's about a meeting, even though I take the logic perspective. Well, for instance, one typical thing that might happen during a game is information update. So what may happen during a game is that moves are made which actually produce information for the players involved. And here's a standard example from the epistemic logic literature. again, my apologies to people who know this standard example, but just to give another connection, a different way of thinking, where logicians would have questions, but you can also think of them about questions about what's the information flow as, for instance, a game of imperfect information gets played, like a card game. So there's three people, John, Mary, and Paul, and they've gotten one card each. John has the red card, Mary has the white card, Paul has the blue card. It's common knowledge that these are the only three cards in play. And now I put this in terms of questions and answers. In a card game, you could also think about something else, calls or drawing a card or maybe flipping a card and showing it, things like that. But I just put it in this conversational form. So Mary asks John, do you have the blue card? And I could ask you now, suppose that she does that. Who knows the deal of the cards now? Where I'm assuming that John, Mary, and Paul all know that the cards in play are red, white, and blue. And the other assumption that I'm making is that each person knows his own card, but doesn't know the cards of the others. So they've looked at their own hands, in this case, only one card, but they don't know the hands of the others. I don't know if anyone from the audience would like to hazard a guess. So after Mary has asked the question, does that actually give information? Is there maybe anyone who knows the distribution of the cards now?
Mary knows it.
Well, the question hasn't been answered yet. So I ask you the question after Mary has asked her question, but we haven't heard John's answer yet.
Paul knows it.
Okay, why?
Because he knows that he has blue. He knows that Mary doesn't have blue, and he knows that John cannot have blue. So, I mean, he doesn't know. Okay, he doesn't know. He doesn't know if John is actually white or red.
Yeah,
he just knows that blue knows.
What Paul does know is he knows what John is going to say. By the way, I'm assuming that this is a truthful scenario. So let's not think about tricky things like rhetorical questions or false answers. So it's natural to think about Paul because the question is about blue. But as a matter of fact, the person who knows the cards now is John. Why is this? John knows that he has the card. Since Mary asked the question, he knows that she doesn't have the blue card. I say it's a genuine question.
Okay, the assumption is that Mary is, used a useful question, so she cannot have the blue card.
Yeah. Of course, there's an assumption in what I'm saying here. So I call that a truthful question.
Okay.
Or if it was a rhetorical question, then no. It would be more complicated. Maybe John would only have a probability.
Then John knows.
John knows. So he knows that it's, actually, what's also interesting, okay, so then John answers no. I could ask you again, who knows the cards now? I'll give you John because he already knew, so he probably hasn't forgotten. So after John's answer, who knows the cards?
Everybody. Because so Mary knows that he has white, John doesn't have blue, so he's for sure John has the red.
I agree about Mary.
So Mary, and then Paul.
Why Paul?
Paul, no, because he doesn't know still if Mary has red.
Yeah. So as far as Paul is concerned, this same conversation could have taken place with red, white for John and Mary.
Paul doesn't know.
So what it ends up with is that John knows, Mary knows, Paul knows. it's a nice, I think it's about the simplest, non-trivial scenario in this sort of epistemic flow, information flow that's nice to think about. And even I sometimes am surprised by what students say about it. Because students actually, one student remarks, look, suppose that after Mary asks John, do you have the blue card? Do you have the blue card? And suppose that John didn't even answer, but that there was some indication that John knew the answer. You know, he might start smiling or something like that. Even that would be enough, because the red card is the only card holder who can actually learn. Okay, I want to continue, but just to show you, you know, this is an issue of epistemic logic and it's an issue of update. So these things can actually be, I should maybe switch on a light. So these questions can be dealt with in epistemic logic. I'm not going to go into the technical details of that, but basically you can describe the information changes that the players go through as, let's say, you could think of this 1 or 2 steps in a game where information is passed. There's a sort of general logical analysis of how you could do this in dynamic logics of information. Again, I don't think it's worthwhile for us to actually look into details of that. I also want to talk about some other things to you. So this I'll just, you know, flash quickly. What we really need here is a sort of logic that can talk about the information update that takes place as questions are asked and answers are given, or if it's not in language, of the information flow that you would see in a card game as cards are played. People see what's put on the table because that tells you something about cards that other people don't have, and so on. And there's actually various logical systems that do that. Maybe one interesting thing about this, so to a logician, what's interesting here is that if you look at this in the setting of games, the least that you will have to think about is combinations of knowledge and action. Because what happens in a game is that there are certain things you know, but that might change as the game proceeds. And of course, in a game, you also make moves. So actions are taken that put you, place you further in the game. Then one of the first questions that a logician would ask is, well, that means that I have 2 sorts of operators in my language. There's K for knowledge of the agent, and there's this operator, brackets A, which we actually read as after action A. It's an operator from dynamic logic. And maybe I have one other question for you. Logicians are always interested in operator interchanges. So whether when you see things in one order, it would also follow that you have it in the other order. So here's an example. Suppose that I know that after action A, phi is the case. So I know now, I mean, I haven't taken action A yet, but what I know is beforehand that after A happens, phi will be the case. So for instance, I'm somewhere in a game, I'm thinking about possible moves, and I know that after I play move A, the effect phi will happen. Does it follow that after playing A, I actually know that phi? And maybe don't think about it in the setting of a game, just think in general. Do you think that this is a valid logical principle? First, I'll say that for lots of actions, this seems totally reasonable. So for instance, I know that if I'm going to take my watch, then after I do that, I will know the time. And it's of course also true that after I take my watch and I look at it, I actually know the time. So that's, I mean, that doesn't say that this is valid, but at least it gives one natural scenario where you would see both things. I also know that if I were to throw my cell phone through the window next to me, right, there would be damage to the glass. Of course, I'm not going to do this experiment, but if I were to do it, I guess you'll agree with me that I would know that the glass was damaged. But does it hold for all actions? Well, at least some actions that have been considered. So for many actions considered in games, the answer is yes. So for actions that you might call epistemically transparent. But if you consider actions that might have side effects on your knowledge, then actually it need not be the case. And some of these actions, you can think of it in general, but have also been considered in game theory. Think of a case like drunken driver. Suppose that the action A is the action of drinking. Here is something that I know. I know that after drinking, I talk too much. Okay? So you could grant me that. That's a reasonable premise. But unfortunately, it doesn't follow that after drinking, I know that I talk too much. That's in fact a tragedy of drinking. And why is this? This is like in drunken driver scenarios where there's a sort of impairment of your cognitive abilities. The action itself has actually impaired your powers of your epistemic powers. So I'm just mentioning this as one more meeting point. So logicians are interested in various interaction principles you could have for knowledge and action. You would also find that as a sort of distinction between game scenarios. Some would actually support this sort of logical reasoning, others wouldn't. And in fact, but that's again technical logic, you can actually figure out precisely under which conditions on imperfect information games, for instance, principles like this would be valid. And what you're going to find is actually strong connections with game theoretic notions like perfect recall. For instance, I mentioned Giacomo Bonanno as an example of a prominent Italian game theorist, also logician. He has studied a lot on this sort of reasoning and various properties of memory and recall that one finds in game theory. Now, of course, I want to make one more step. We're still not in actual game theory, because I've now talked about game forms, actions, knowledge, things like that. But I haven't talked about preferences and maybe goals that players have. So of course, then we get into the area of backward induction. Now, I guess I don't have to explain to this audience how backward induction works. But for instance, this is an example. It may not appeal to game theorists because it's too simple, but it appeals to logical audiences. Suppose that I have two players, A and E, and A can actually choose left. And then A gets 1 and E gets nothing. The other option is for A to go to the right, give the turn to E. E can go left and get 100 and A gets nothing. Or E can go right and both get 99. Now, if you compute a solution to this by backward induction, then actually what you're going to find is that working a bottom up, you first look at what E is going to do. Well, E has a choice between getting 100 or 99. So rationality would probably tell her to choose the one to the left. So she's going to go left. Since A can see this coming, he would actually believe that if he gives the turn to E, he's going to get nothing. So therefore, it's most rational for A to actually go left. And the game ends in 1-0. And to quote another famous Italian economist, of course, that's not Pareto optimal, because 1-0 is, of course, worse for both players than the outcome 99-99. Now, game theoretically, this is not an interesting example, I guess, and also not economically. But to a logician, there's a world of questions here, because there's lots of notions in the scenario which I've just told you, which have actually been looked at in philosophical logic, and which pose all sorts of issues. The argument presupposes that the players know the structure of the game. We also have to be able to reason about their preferences. So some sort of preference logic is involved. There's also beliefs, because notice that if A is going to go left, he's never going to see in reality what E is going to do. So the best that he can base his behavior on is a belief about what E is going to do. So lots of notions play here, even in a simple example like this. This is in fact why some prominent philosophical logicians have actually suggested also for logicians to look at games, because even the simplest games seem to combine the whole agenda of philosophical logic. So that's, of course, for us economists, I guess, already knew this. So let me skip the backward induction algorithm, and I also don't want to say too much about these slides. There's various styles of analysis of the backward induction algorithm, which you can find in the references that I gave. You can analyze them in more detail. Then you get into fixed point logics, and I'm just showing these formulas to impress you. But basically, it is possible to actually analyze what backward induction does exactly in terms of fixed point logics of computation. It's also possible to think about backward induction in a bit more general terms, because you might also think, I'm not so interested in the actual details of how the algorithm works. But what backward induction actually does, if you look at its output, what it tells the player is that among the various actions that the player has available in the game, there are some best actions. So among all the actions, some are best, according to the underlying reasoning of backward induction. And it's a natural question. You could also try to axiomatize in logic. Suppose that you have a structure where you have actions for which you have a standard logic, like a modal logic. You also axiomatize those actions plus the best actions according to backward induction. I give you one axiom that's actually valid there, but it's actually an open problem what that modal logic is. Now, the last topic I want to say something about in this talk is also goes back to this backward induction example, because I said, look, if A goes left at the beginning, that's based on a belief. It cannot be based on knowledge because he doesn't know what E is going to do. The only way he could find out and really know what E is going to do is by moving right, but then it may be too late. So I promised the organizers to say something about the notion of belief and how logicians think about that. Now, I just want to say something about this, and again, I put my caveat. I'm going to give you one style of thinking about beliefs, which is popular among, well, in my logical circles. But again, I'm not saying that that's the only way you should do it, because another way of looking at everything that I'm saying here would be in terms of probability, which I won't pursue. So a simple and currently popular model of belief works as follows. You could think of your knowledge as a range of possibilities that you see. So for instance, suppose that you look at my picture at the bottom. Look at this situation with 4 possible worlds. So 1, 2, 3, 4. For each world, I've indicated for 2 proposition letters whether they're true or false. So actually what you're seeing is all 4 possible combinations. Now, beliefs, in the semantics I'm talking about, called plausibility semantics, is actually encoded in an ordering of plausibility that you have among the options that you see. So in terms of what you know, you only know what's true in all 4 cases. But now plausibility in this case. What you actually think is that world 2 is more plausible than world 1, and world 3 is more plausible than world 2. Okay, that's just, I'm giving you that. Of course, you could have reasons for that, but just in the example. And world 4, I've put in an incomparable position. So 4, I'm also considering, but I can't really place it in terms of greater or lower plausibility with respect to the other 4. Now, what would you believe in that situation? In plausibility semantics for belief, the idea is that you believe phi if phi is true for all points t that are maximal in the ordering. I'm looking at the first 2 lines of this slide. So to immediately go back to my picture, what would the agent believe? Well, what are the maximal worlds in the ordering? They are the worlds for which there is no more plausible world. So there's only 2 worlds which satisfy that description in this model, namely 3 and 4. 3 is at the end of this plausibility sequence. There's definitely nothing more plausible than 3 in the ordering. And since 4 is incomparable with the rest, it also has nothing that's more plausible. So in terms of belief, knowledge requires the agent to look at all 4 situations, but belief would only ask the agent to look at 2 of them, namely 3 and 4. And for instance, one thing you would see in this model is that the agent believes that P, because P is actually true in both 3 and 4, right? So in the most plausible worlds of this model, he will always see P, but he doesn't believe Q or believe not Q, because both Q and not Q are possibilities when you look at 3 and 4. So that's how this belief semantics works. So the thing to just understand here is that belief has to do with the plausibility ordering that you have on all the options that you see. And belief, in a sense, is less demanding than knowledge, because knowledge says that something has to be true in all the options that you see. Belief, more opportunistically perhaps, says, I just look at the most plausible ones, and I'm going to believe what's true there. Okay. Belief is not the only notion we can define here, but I'm going to skip that. Now again, if you think about games, agents might have beliefs. Those beliefs could be in an imperfect information game about where they are in the game tree. For instance, I might have beliefs about the cards that you're holding, but it could also be beliefs about the future of the game. So I could have beliefs about what type of player you are, so what you're going to do in the future. That means that as the game proceeds, my beliefs can change. And that's a sort of interesting issue in the dynamic logics that I'm interested in. So there's various ways in which beliefs can change as new information comes in. One of these sorts of information is called hard information in the literature. It's information which you consider 100% reliable. Like, for instance, suppose that you're playing a card game and you see that your opponents put a certain card open on the table. Right? That's hard information. That means none of the players, the other players, actually has that card. It's just there. Well, it's possible to analyze how beliefs change under hard information, and there's various logics that do that. These can even already lead to interesting scenarios. So maybe this one, that's actually a little scenario that was discovered independently in computer science, game theory, and I believe also in philosophy somewhere, called lying with the truth. So take my plausibility model to the left. There's 3 worlds. And let that black dot be the actual world. But the agent has the following plausibility order. The agent thinks that the world in the middle is more plausible than the one to the left. So the agent is a bit off as far as the actual world is concerned. And he thinks that the world to the right, so the 3rd world, is actually the most plausible. This agent believes that P, because he only looks at the most plausible worlds, which is the world Q3 to the right, and P is actually true there. So we as outside observers could say, this agent has a correct belief, be it for the wrong reasons, because he's not looking at the actual world, he bases his belief on the world Q3. Okay. Now let's suppose that we give the agent true information. And we give the agent the true information that world Q3 is actually not an option. So we tell the agent not Q3. This is true information because it's true about the actual world, which is Q1. Right? So we're actually telling the agent something about it. You know, it's right. We're not in Q3. But notice what happens now. Then the agent will rule out Q3, so his new plausibility model will look like the one which I have to the right. It has only 2 worlds, Q1 and Q2. And now the agent actually believes that not P, because Q2 has become the most plausible world. So you can see why this is called lying with the truth. You tell the agent something that's true, but you actually change the correct belief about the actual world into an incorrect one. So there's lots of interesting phenomena here that can actually be studied. There's also other ways in which beliefs can change, which I'd be happy to answer in question time. For instance, in addition to hard information, there's soft information. but I'm not going to go into details about that here. There's also logics for this, which again, that would be something for a very technical talk. And maybe the only thing I'll say to conclude this part of my, I think I need about 5 or 7 minutes more. Is that okay? If I leave some, I want to leave some question time.
Yes, sure, no problem.
Okay. I just want to show how these logics of belief change could actually come in again when you think about games. So I'll start with, well, I'll actually take backward induction as an example 2 times. Let's first think about the actual backward induction algorithm. So one way you might think about how that algorithm works is actually that it's something that we run before we play the game. In my jargon, oh, well, I don't know where that slide is, but it's actually a pre-game activity. So backward induction may set up our expectations about what's going to happen in the game. We haven't played it yet. And you can think of that as a process of creating beliefs. Now, of course, the process of creating beliefs has to be driven by something. And one thing that that's a typical driver for backward induction is that you believe that the players are rational, or maybe to be a bit more precise, rational in beliefs. So this is a point that's not always appreciated when people talk about rationality, although of course in the game theoretic literature it's standard. People often say that rationality is taking that action which is best for you. But of course that misses out a feature because I may not know what's best for me. So rationality is, of course, in reality, choosing that action which I believe to be best for me. That's the only thing I can do. And now you can think of the assumption that players actually play rationally, according to rationality, and that again according to their beliefs, as a process of belief creation. Because you might say, first you have the game as it is on the left. But if you think about rationality of the players, then you're actually going to expect that E is going to go left rather than right, for the reasons which I gave earlier. And you could think of that as the creation of a plausibility ordering. You now think it's more plausible that E goes left than that E goes right. But then, if you now repeat this thinking, you're actually going to say, in the situation of A, I want to act rationally in beliefs. What are my beliefs? Well, my belief is that if I go left, I get 1. My belief is, I'm talking about the game in the middle, my belief if I go right is that I will get 0 because the most plausible history in the game in the middle is the one that ends in the middle point, 0, 100. So, of course, I don't know that I'm going to end in 0, 100, but it's what I believe. So rationality in beliefs will actually tell me that in that case, I'm going to go left. And that, again, you can see as plausibility creation. What backward induction actually does there is it tells you that then the outcome X is more plausible than Y, more plausible than Z. Notice that still everything could happen in the game, right? I haven't ruled out anything, but I've created a belief structure, a plausibility structure. Okay. The other backward induction connection I wanted to mention, which actually has been discussed a lot also by philosophical logicians, is the paradox of backward induction. So think of the first scenario I gave you as what you might do before the game. Now think of what you do during the game. And there's an interesting discussion, there's been an interesting discussion here, for instance, between Stolnaker, prominent philosophical logician, and Robert Aumann. So suppose that you actually play the game, and suppose that somebody deviates from backward induction. How are you going to interpret that? Now you're not before the game, you're not creating your expectations, you're actually experiencing the game as it's played. So let's suppose, for instance, that in the game which I gave here, A plays right. What is E supposed to think? So A has deviated from backward induction, maybe against E's expectations and so on. So what does that off-path play mean? maybe. The backward induction algorithm, notice that it goes bottom up. So it would actually recommend that E analyze the rest of the game by backward induction. That's the bottom-up nature of the algorithm. But of course, something's taken place. So E has more information. E has the information that A deviated. What does that mean? Well, Fries Aumann has often said that this means that A has made a mistake. And then there's a nice paper by Dov Samet who says that's maybe okay, but if you have a game tree with 1 million nodes, and you still think after 900,000 deviations that A has made 900,000 mistakes, then A is not making the mistakes, you are. That would probably mean something. So maybe it's something else. Maybe A is not playing BI. Maybe A is sending a signal that he wants to tell you something about the rest of the game. The Stolmaker versus Aumann debate was that Aumann has a theorem which says that if there's common belief in rationality, then the players have to play according to backward induction. Stolmaker said, no, that's not true. But actually the difference was not a conflict in mathematics or even a conflict in philosophical position. It's just a conflict in the idea of which belief changes the players will undergo during the game. And Stolmaker would actually say that in order to specify the game as it's played, you need to know the player's belief revision policy. Okay, that was an example of a live discussion where maybe people have different sides between a game theorist and a philosophical logician. But again, it demonstrates this topic of belief revision and its importance. I think I'm at the end of what I wanted to say. I stayed at a very high level of giving connections, but let me summarize. I started with classical evaluation games and just suggested that there's interesting connections there between the basics of logic, truth, laws, validity, and basic issues about games. Then I actually said, but look, when we start looking at the players, then there's actually lots of other things going on. One is that they just pick up information. So we need to get into combinations of thinking about games, epistemic logic, dynamic logics of information, and so on. And then if you get into real game solution algorithms and real game scenarios, you're going to find beliefs everywhere. And I've just skimmed the surface by telling you that that's a very fertile meeting ground of game theorists who are interested in that and logicians who are still in the process of developing all sorts of logics of what belief is and how it changes. Thank you.
So thank you, Johan. Thank you very much for this talk. I think the talk was perfectly suited for the occasion, since I think it has been very interesting to students, but of course it was insightful also for more experienced scholars. If I have to think it egoistically, it was very much suited for me and Alessandro because it resonates a lot with what we are up to now. So thank you very much for that. Now we have time for questions, so I suggest that if there is somebody who wants to speak, can just activate the audio and ask a question if there are.
Okay, maybe I can start.
Yes, Alessandro.
It basically goes back to the discussion we also had last day. So it seems that at the base of the connection between the last type of games you presented and logic, there is still this concept of rationality, right? And as you said, so I cannot actually say what is best for me. I can only say what I think is best for me. So my question is there any other horizon where, rationality can actually live, and there is a way in which logic can, say, define rationality beyond, let's say, the concept of, let's say, best choice or best allocation. Yeah. So there is another territory that we can explore beyond the concept of maximization of utility or whatever. Okay.
Yeah. Yeah. No, I understand your question, and I also know that this is important in your project. So, my personal opinion, right? Because you asked me, can logic do this or that? I'm not speaking on behalf of logic. I'm speaking on behalf of myself. But I don't think logic is tied to the notion of rationality as optimizing behavior in the standard sense. So, in fact, the way I think about rationality, and I had a slide about that, is actually the way I think about rationality is it's about choosing a certain balance between your information, your preferences, and the actions that you're going to take. I think it's rational to have a sort of idea how you want to balance these three considerations. But exactly how you want to balance them, I don't think that logic is going to tell you that that balance has to be that you go for the best possible action given your beliefs. For instance, I define with an analysis, and some of my students have been interested in that, in terms of satisficing, right? If you take Simon's notion, so we don't go for the best, but we go for good enough. And I could also imagine, for instance, in some of the other literature, at least, that I haven't surveyed here, the notion of preference often disappears a bit, and logicians think in terms of goals. So basically, rationality is about a sort of balance between your information, the actions available, and the goals that you're trying to achieve. And if you think in those terms, optimizing utility or something like that need not even be the best notion. It's about realizing your goals in some sort of satisfactory way. Is this to the point, your question?
Yeah, I mean, it is actually, because I mean the problem we face in our project with Ricardo is exactly this one: try to find a different way to define rationality, at least from a subjective point of view. And if you go back to your example, clearly, if I change the perspective of the game, for example, here, I just think that this is not one-shot game. I just think it's a repeated game, for example. So the scenario changes completely.
Of course, yes. This is yes.
So I basically may have, let's say, preferences for social outcome instead for, let's say, individual outcome, just based on the structure of the game, on the perspective of the environment in which we live, right? Now, the answer you gave on rationality is, I mean, to me, it's satisfactory, because I still believe that we cannot just unify this definition under just one, let's say, concept. And clearly, there are many ingredients that enter, and it must be, let's say, related to the environment in which we are, right? Something that usually economists don't do.
If I may interrupt you for a moment, look, Alessandro, I believe it's called the Oxford Handbook of Rationality, which is full of chapters about what rationality might mean. So there's definitely a sort of lot of legitimate spread of opinion. And with some colleagues, I'm actually contributing a chapter to the MIT Handbook of Rationality, because maybe rationality in Oxford and in Boston is not exactly the same. So that's two handbooks. And also one of the points we make, this is with Sonja Smets and Van Rong Liu, we also make this point that one should have a sort of more looser attitude towards what rationality is. It's also a notion that has so many different dimensions.
Exactly.
And it's very important to set it in the right way.
And I also believe that there are some that are also hidden. For example, emotions, something that belongs more to the sphere of psychology. So. And I mean, this also may change or may affect choices and the way in which we behave.
I couldn't agree more.
Thank you.
Okay, thank you. Are there other questions from the audience? If not, or in the meantime, somebody else is thinking to a question to ask, I might have just a very tiny curiosity, which is maybe of a very technical level. You mentioned the plausibility models, and of course you also mentioned the probability models, which give you an alternative approach to model beliefs. Is there some standard result connecting the one approach to the other? Because I mean, I can see you can easily define a plausibility model out of a probability one. Probably you must have conditions on the ordering if you want to get the reverse equivalence or not.
Yeah, okay, very good. So now we get into more technical details. And again, I apologize. I gave a high-level talk. Of course, there's a lot that one could say. Yeah, so there's some work on connecting these things. Indeed, as you say, one could extract a plausibility order from a probability order. And okay, but it's actually a bit of a complicated issue, because even if you think in terms of probability, okay, suppose you look at the points or the outcomes in your probability space, and you would probably say something like the outcomes, let's think of a finite probability space. Then you would probably say that the outcomes with the highest probability are going to be my highest plausibility. Okay, something like that. But now notice that a probability, the way I often think about this is plausibility is aristocratic, probability is democratic. So in aristocratic thinking, like in plausibility models, you only look at the most plausible models. So in a probability space, on a simple-minded thinking, you only look at the worlds which have the highest probability or the greatest weight. But actually in probability, if you think about the probability of a proposition, it can be very democratic. Maybe there's one world which has probability, let's say 1/3, and you have 1,000,000 worlds which all have very low probability, but they add up to 2/3. You see what I'm saying? Then in terms of probability, those small worlds, each of which is insignificant, together actually drive the probability. They win against this highest probability world. Whereas in plausibility, that doesn't happen. If the most plausible worlds vote for something, then what the others do doesn't matter. So there are some interesting issues here about how you want to get this mathematical comparison right, but there are mathematical comparisons. I can send you references. The other thing is that there's psychological research suggesting that people are actually capable of reasoning in both ways. I wish I had put this slide on my presentation, but I can send that to you later. There's actually a nice example, I believe it's called the Georgia coast. So suppose that you so suppose that you show people the coast of Georgia and there's a hurricane approaching. And the question is, should I leave my home and fly inland? In the one map, we show your region as an actual chunk of Georgia. And we actually show the other regions at the same high level of detail. And let's suppose that among the other regions, there are definitely bigger ones, so larger counties, let's say in Georgia. Then what people are going to say is that they don't need to leave because they live in a region which is smaller than the other chunks which they see on the map. Suppose now that you actually subdivide these larger chunks into sub-counties, so you show them essentially the same map of Georgia. But what you've done is you've left your region the same, and the others have been subdivided. Then actually they say they should leave. Now in probability, nothing has changed. I've only given more fine-grained information. So that's very interesting to see that, maybe under different presentations, probabilistic views or plausibility views could diverge in what people react to.
Okay, thank you very much. I think you managed to turn my uninteresting technical question in a much more interesting one. And is there any other question from the audience? Is there anyone else who wants to ask a question to the speaker?
If not, I'll just advertise. So if you want to take a quick look, then you can actually look at logics for analyzing games in the Stanford Encyclopedia of Philosophy. That's actually an article that has a lot of information on what I've talked about in this presentation. So various sorts of logics that can tie up with game theoretic structures. The evaluation games that I started with actually demonstrate something else. It's more a case where you use the games to understand logic. There's also an entry in the Stanford Encyclopedia written by Wilfred Hodges and now updated by Jouko Väinänen, which is actually on logic games. You can think of that as a companion to the logics for analyzing games. So if you want the total picture, you could actually look at these two entries of the Stanford Encyclopedia.
Thank you very much, Johan, also for these references. Actually, failed to mention your book, which contains a lot of information, also about what you've just presented to us. So I assume there is no more question. So I think since it's more or less the time we wanted to reach, I think we can just say thank again to the speaker for this very interesting talk. It was a pleasure to host it, Johan.
Sure, and keep in touch about your project. And of course, I wish you all the best in these strange times. And I envy you as you're enjoying walking through the empty streets of Florence.
Thank you very much, but it must be the same in Amsterdam too, I think.
Yes.
So we envy you for that.
Bye now. Bye.
Bye. Thank you.
Bye to everyone. Thank you for attending.